Hello?
Yeah, Madhav, can you hear us?
I can hear you very well. Oh, fantastic. Yeah. So just 2 more minutes to start. I think, Santosh, are you around? Hello, Santosh? Dr. Jyoti?
Yes, ma'am, I'm here.
Okay, good, good, good. Okay, 2 more minutes and then we start. We have a lot of participants here, and many of us are following in the YouTube link also. And I can see Dr. Singhi. Hello, sir. And so many students and faculty. That's really nice. Uh, good.
Not now.
Santosh, I think you can start. Santosh, please see the chat box. Professor Singhvi has a message. You can please share it. Okay, please go ahead.
Shall I put my presentation now or later? No sound. No sound, ma'am.
Santosh,
Now I can.
we cannot hear you. Dr. Santosh, please see that we cannot hear you.
Okay. Good afternoon, everyone. I am Santosh Shah, Treasurer AOQR. On behalf of Dr. Banda Prasad, President AOQR, BSIP, and Vice President Dr. Pradeep Srivastava, Wadia Institute of Himalayan Geology, our office bearer, member, and founder members, honorary members of AOQR, Professor A.K. Singhvi, Professor L.S. Shamyal, Dr. Hema Ashutan, and Professor Viswas S. Kale. Our ECR team and my own, I welcome you all for third webinar in the web series of AUQR ECR. Today's talk will be delivered by Dr. Madhav Kumar Murari from IUAC, New Delhi. So before we begin, I request all participants to kindly mute your mic and also turn off your camera to manage the bandwidth of the internet. And I also request, please avoid accidental sharing of your screen during the presentation. Since for the 2 months, like this September and October, AOQR team, along with the ECR AOQR team, is organizing webinar series on the development of quaternary science. First talk in this series was delivered by Dr. Amjad Laskar from PRL, Ahmedabad, And last week, on 14th of September, a talk was delivered by Dr. Oliver Rahman from NCPOR. And he talked on the topic ocean acidification threats under high carbon dioxide worked, a lesson from the past records of ocean pH. That talk was attended by 223 participants, and since the talk was live streamed in YouTube, so till date it was viewed by more than 450 viewers. We received feedback from the participant, and 117 participants evaluated that talk as excellent, and 51 as very good, and 53 as good. So overall rating of last week talk is excellent to very good. It was not only attended by participants from India, but it was also participated from other countries like Israel, Pakistan, Philippines, Taiwan, UK, and Nigeria. And about the feedback of last week talk, participants found that talk was very interesting, and some PhD scholars also mentioned that they learned a lot and they want to apply all those methodology and information in their PhD work. Participant also pointed that question and answer session had interesting point and hence need to be addressed for additional time, and more time should be given for discussion. So in this regard, we would like to inform you that from the next talk, we would like to keep first half an hour for panel discussion so that the participant can discuss with the previous presenter. So next week we can discuss with today's presenter, Dr. Murari, in next week webinar. So many of you are interested to join AOQR, and questions has been raised how to join AOQR. So we almost finalized our website of AOQR, and you will get all the information about how to join this AOQR's forum. And you can email us in aoqr2019@gmail.com. I will also share the email in chat box. Well, now I would like to invite Dr. Murari for his talk, but before that, I would like to introduce Dr. Murari to the audience. Well, Dr. Murari, Madhav Kumar Murari, presently working as a scientist E at Inter-University Accelerator Center, that is IUAC, at New Delhi. He completed his MSc in physics from Dr. Bhimrao Ambedkar University, Agra, in 1998. Then he completed his PhD from PRL in 2008 under the supervision of Professor A.K. Shinghvi and Professor K.P. Subramaniam. He was also a postdoctoral fellow at PRL during 2008 to 2010, and he was postdoc at University of Cincinnati, USA during 2010 to 2015, and worked with worldwide renowned researcher Professor Lewis A. Wen. He also did his postdoc at Germany also with Professor Marcus during 2015 to 2019. Dr. Murari, being a physicist by education, but now with his expertise in OSL and TCN, that is optically stimulated lamination and terrestrial cosmogenic nuclide dating of rock and sediment, he is now a quaternary geochronologist and geomorphologist. He is applying these techniques of dating techniques toward paleo-environmental reconstruction and landscape evolution. He has also experience of infrared radiofluorescence, that is IRF, which is considered as an alternative elimination dating method for sediment dating application using Feldspar mineral. Presently at IUAC, he is taking responsibility of geochronology project to develop geochronology-oriented new scientific programs mainly focused on quaternary period and research and development toward improving geochronology methods and application. He has published 23 research papers in various international research journals, and he is actively participated in organizing in various workshops and conferences, not only in India, but also abroad. So now I invite Dr. Murari to talk on a topic, Cosmogenic radionuclide application to geomorphological process. Dr. Murari, kindly share your screen and proceed your talk. Thank you very much.
Okay, thank you, Dr. Santosh. It was a really long introduction. Okay, can you see my presentation? Then we can start. Yes. Enter screen.
Yes.
Yeah, is that visible?
Yes, sir. Please, sir.
Yes. Thank you, Dr. Santosh. I think this is very good platform to discuss what we are doing. I really appreciate that this platform is arrived. I heard the last speaker. It was very nice to hear about boron isotope, how it reflect the acidity of ocean. So, with that, thank you everyone, and mm, once again, good afternoon to everyone. I'm I'm trying to manage myself. Okay, first slide is always like make it nervous. So, what I'm going to talk today, title of talk is Cosmogenic Radionuclide and application to geomorphological process and what are the issues. So this is the little bit I added to my title. So what I'm going to talk, so geomorphology, mostly I think I will dwell upon cosmogenic dating and what are the issues with the dating methods and why sometimes they make discrepancies. So mostly this the research is on Himalaya areas. That is the most dynamic field where geomorphological process takes place very fast. So we will start with the paper published by Shukla et al. In 2020. Here I will define what was the problem. So what you see, the optical chronology, and they compare the beryllium chronology. What you see, can you see this line, the blue lines, or you can't see? Can anyone can tell something? Okay, no problem.
You can see Murari, go ahead. We can see that.
Okay, because I can't see on my screen, that's the issue. No problem. So what they compared, what they found, the OSL ages are much younger than 10 beryllium surface exposure ages. Something like magnitude of order. So I thought, why not let us discuss the issue, what issues are with 10 beryllium dating method and what we can do about it. So this is the same area. Another paper was Dodge et al. In 2010, where they studied the same area, but interpretation are different. So these are the area they studied. And now I will outline my talk, how I'm going to do it. So you see that there is a problem of geomorphological process and we get discrepancies. Why cosmogenic dating method is not comparable to OSL method? What are the issues with cosmogenic as well as OSL dating methods? So this is not like one dating method is bad, one dating method is good. Let us discuss openly what are the issues. So cosmogenic dating method first. So how, this is a little history about the cosmogenic radionuclide method. First, cosmic ray measurement started in 1911 by Hess. And then in 1949, first measurement of natural carbon measured by Chicago group. Then 1951, first publication came from Arnold and Levy. These are the landmark things. And then 60 to 70, application to extraterrestrial material. Just remember, extraterrestrial material means meteorite or lunar sample, extraterrestrial material. This was applicable because they interact with primary cosmic rays and you get enough amount of the isotopes. And then in 1977, AMS reinvented by Muller. And then on, in 1986 to now, the development and towards the surface exposure dating. Here the large Jola group started. And now the basic of terrestrial cosmogenic method, there are comprehensive work by Lal and Peter in 67. And Lal, we are very fortunate. The Lal was PRL director, and I was part of the PRL once upon a time. Sorry. So Lal published this paper in 1967 to see the cosmogenic nuclides, how they can interact with terrestrial material. And a little bit about the cosmic rays. So what you see here, the bunch of nuclides and mesons. And where you will see the upper part, I will take laser pointer just a minute. Okay. So upper atmosphere have cosmic ray particles. And when they come to the Earth, they interact with atmosphere and they disintegrate. And then finally, they come to terrestrial level, like they interact with the Earth. These are the basically secondary particles. And what you see here, another part, here you see the attenuation of particle at low latitude is something like 150 gram per centimeter square. Low latitude means they have to cross more length, more atmosphere pressure. And then at high latitude, what you see, the 130 gram per centimeter square, the attenuation will take place less here at high latitude, and low latitude attenuation will be very high. So cosmic ray will produce here more isotopes than the lower latitudes. So the cosmic ray interact with the boulder or a rock where you have a silicon oxide, and there they produce a lot of isotopes like neon 26, 10 beryllium, carbon 14. But why they are important? Because they have a half-life. What you see, for example, 10 beryllium has 1.5 million years, and aluminum 26 has 0.7 million years. So this half-life is more important to find the time information from the rock. So far, so good. It is very good. So mostly I will talk about 10 beryllium and 26 aluminum. So what we see, finally, the great equation came here. What you see, the concentration of particle, concentration of these isotopes will start developing in the rock. How? There is, you see the division, prior exposure, and production rate, and erosion rate. What you see here, the prior exposure, the concentration, this equation tells a lot, because here is the issues, here are the issues. I will spend 2 minutes here. So what you see, the concentration of the isotopes will depend upon the prior exposure to boulder. Let us say boulder was exposed earlier, and this has some information. That means it is inherited. And from zero, the production started here, then P, that means production started itself there when boulder was just like eroded properly, so this doesn't have any information prior to the deposition at this place. So we want to get the information when this boulder exposed. Excuse me, can you hear me? Hello?
Yes, we are hearing you, don't worry.
Yes, we can hear you.
But somebody is asking something?
No, I guess someone is unmuted.
I think it's some of the participants. Please switch off your audio, please. it's a request. We've been putting it everywhere, but some people are still with audios on. So Madhav, I think you can go on.
Okay. This sequence is important. I want to emphasize here some more part. Okay.
Yeah, Jyoti, please check who is unmuted and remove them. Please.
Okay. Can you see my presenter still or no?
Your presentation is not visible. Please show your presentation.
Can you see now?
Yeah, it's clear. Kindly make it full screen.
Full screen I will do. Okay. Okay, so what we see here, the different part of this equation is responsible for different type of production. So this is inherited. The first one, sorry, just a laser pointer I will take. First one is the prior exposure. So it has some information from back. And this is where it started, from zero. And there are some factors where, like erosion of a boulder, how it takes place and how fast erosion, and this will take care of these parameter mu and epsilon. The erosion and attenuation, this will take care. If sample was buried, let us say boulder was buried, then that means there was no exposition. So exposure to cosmic rays. So this factor will take place of if sometimes sample was buried or not buried. So these are the factors. But what we do in case of glaciated boulders, we calculate the exposure age. And in exposure age, what we have a production, and we assume there is no prior information. We assume. So this factor will go away. And then we also assume that there is no burial. So this factor will also go away. So what you see here, the net concentration, we should calculate with this. If this is ideal case, this is but very ideal case. So now, what we see here, cosmogenic radionuclide is very good because the age limit is very high. You see here from 10⁻² to 10⁸. Looks very nice, but there are some problems. So I will go to now complexities. What are the complexities? So what you see here, too many parameters. The cosmogenic radionuclide depend upon the production.
Dr. Murari, you please continue.
Hello?
I will go and remove the person which I just found.
No problem. So what is happening here? The beryllium, this is the production of beryllium atoms in quartz. And these are different people measured. What you see, the atoms per unit gram, per unit year, what you see, this varies from 6 to 4. Maximum is 6 and minimum is 4. So different people measured at different concentration from the quartz. So what we see, if we propagate this uncertainty, let us say 6 to 4, is something like 30%. So this production is 30% change. And when 30% production propagate to the time information, this will propagate error further. So these are the basic issues. The production is not decided. Everyone has estimated different value of production. So another issue. So this was so production is not well defined, but not only production, but you see the many complex problem. Energy spectrum is not defined. So this will further introduce the introduce the error. And further, the field calibration sites are very limited. And regional site for Himalaya, if we see, we don't have any calibration site for Himalaya. Effect of magnetic field on cosmic ray flux. If we don't take care of magnetic field variation, this will also change, and this will give feedback further. So these many complex problem is there existent radionuclides. And what they have done, so I will discuss. So what you see here, what are the other problems? You see here the boulder is here, and topography will have a different shielding. If we don't care about the topography of where we collect the sample, if topography increases, slope is increases, that means increase the shielding. The cosmic ray particle will not come to the boulder. When they don't come to the boulder, they won't produce the proportional amount of radionuclides. Similarly, so other problems like vegetation cover, if you sample here, the cosmic particle will be absorbed and the less production. If you see the snow cover, Himalaya is prone to have a snow cover. If it's too much snow cover, snow will absorb the particles, and we can't have the concentration what we expect. And similarly, the surface lowering, let us say, when boulder exhumed, that means it came from the inside. And then when it exhumed, that means it was buried for some time. When this was buried, that means this will give the lower age because cosmic ray was not there to produce the concentration. Similarly, surface slope. So these are the many problems. When surface slope, that is boulder can roll over, and we don't know when it was there. So now, so these are the complex problem with the radionuclides. Just remember few of them. And now I will come to what they have done. So this is another thing, the magnetic field, where is high latitude, low cutoff rigidity. Low cutoff rigidity means when cosmic ray enters, they can enter very freely. So you have a low magnetic field, they don't have to cross magnetic field all the way. And when you have a low latitude, there is a high cutoff rigidity. So the low production here, high production here. So now what they came up with is scaling scheme. So because the radionuclides have different production rate and different problems. So what is the, now I will discuss the scaling schemes, but they still have some problems. So what are the scaling schemes? So these are the 5 scaling schemes we use to estimate the cosmogenic radionuclide method to estimate the production. So these are the mainly depend upon the production mechanism, how production mechanism takes place. So lal and stone, still this method is much better. So lal and stone is based on the latitude and altitude. It correct for based on latitude and altitude. So, but there is a one thing, it doesn't take care of magnetic field variation. Magnetic field variation doesn't mean now, that means paleomagnetic field variation. Because in past, magnetic field also keep changing. Then came Dirichlet et al. The scaling factor is function of cutoff rigidity and atmospheric pressure. The production rate vary with time according to magnetic field. Here, paleomagnetic field keep changing and it will take according to the past data. And Dunai et al., it is same like Dirichlet. It also take care of cutoff rigidity, atmospheric pressure, and the magnetic field also vary with time. And Lipton et al., he mentioned that not only magnetic field and atmospheric pressure, but it also take care of solar modulation, depend upon the changing of solar activity. And further, Lal, Stone, and Nishizumi, they combined together because Lal Stone was working much better because they measured their measurement was based on neutron flux measurement, and this combined.
Madhav, I'm sorry, I
Yeah.
can't see your presentation.
Your presentation
Something
is-
self-centered and it is interrupted. Can you again share your screen, please?
Okay, nobody is saying from where it was.
Yeah,
Samuel.
just now.
now.
In a minute.
Is okay. Okay. So let me stop once. Thank you, Raviul. Can you see the presentation? No?
No, not yet.
Not yet. Let me stop again. Okay, a window. Can you see it now?
Yes, please.
Okay, thank you.
Yes, okay.
Oh, thank you. Please remind me if something goes wrong, please.
Sure. Don't
Okay,
worry.
no problem. So from here I should start from back or from the same slide? Yeah.
From the same slide. Yes,
Okay.
this one.
So these are the scaling scheme. These are five main scaling scheme are used to correct for the production mechanism of isotope, beryllium isotope and aluminum isotope, or any isotope which are produced by cosmic rays. So Lal and Stone worked on latitude and altitude scaling factor, but it doesn't take care about magnetic variation according to time. So that means he considered nuclear production is constant over the time. And Dirichlet et al., again, they introduced the magnetic field change. That means in past, if magnetic field is changing, they have an adjustment to correct for it. Dunai et al., they have similar like Dirichlet. But Lipton introduced another factor is solar modulation, because solar activity changes and cosmic flux changes. The further, Lal, Stone and Nishijumi was combined because this method was always working better. And because Nishijumi has an arrangement of paleomagnetism, so they develop a scaling factor by using Lal, Stone and Nishijumi, the data. Now, if you see, it looks very good when we see the data is comparable and very nice. If you see here, the atmosphere pressure data has collected from different stations. And model is able to predict within 5% most all over the world. If you see the model, P10 model within 5% and measured at P10 stations. So within 5%, if you see the all dots are able to measure. And again, there are few less than 5%, few greater than 5%. But the small dots are a large amount of small dots where it's 5. Yes. So now what you see, this data shows the variation in production, measurement, and calculated by the model. So what you see here, these are the two models, Lal Stone and Lipton Sartor nuclide dependent. So this is the paper by Phillips et al. In 2016. I wrote to 10 extra, I'm sorry. So what you see here, the measured beryllium is here at 1. So what we see, the computed with the model is like varying up to 20%. And mostly the data is upper part. So that means the product, what we are measuring with the model, it is always always at higher side. There are very few numbers which are lower side. So what we see here, so that means we are little bit, the models are a little bit estimating the production is higher. So production higher means cosmogenic nuclides should be, cosmogenic nuclide will overestimate by the 20%. So this will further introduce the error. Similarly, this was measured by beryllium concentration, and now what they have seen, how it varies with time and elevation. So these are the two models they compared, the stone and distillate. The stone has no paleomagnetism arrangement, while distillate has paleomagnetism arrangement. So they want to compare how this changes, the value of the ages, how it changes. So you see the contours, the lighter is TST TD is 0.9 for the sample locations, and the darker is the 10%.
Sorry to interrupt you. I request Dr. Girish Chandra Kotiari to please stop your presentation. You are presenting your screen.
Okay.
No, I think Dr. Girish Chandra Kotiari presented his screen actually, and your screen is not visible now.
My screen is not visible?
No, it was. Now you have to represent your screen. And
No
also
problem.
kindly hide your something is coming like meetgoogle.com is sharing your screen. Just hide that one, okay? When you
Hide what?
no,
This
first present your screen now,
okay.
because someone presented his own screen. That's why
Okay.
your screen is now interrupted.
So can I do the spotlight or
No. Just present now.
entire screen?
Yeah.
Okay. And this is here.
Yes, it is coming.
This hide, I don't know how to.
Just hide that one. Just click.
If I
hide that
hide
one, it will
this,
go on.
stop presenting.
Yeah.
Shall I try?
Okay,
Can
now
you
it's
see?
okay. Okay.
Can you see the presentation?
No.
This is the.
Just move that things little
Okay.
bit. Yeah, now it's clear.
Now it's clear. Okay.
Okay, thank you. Please
So what?
carry on.
Okay, thank you again. So what we see here, stone and distillate, the model they were compared, and based on what data they have. So what they see, the value of production increases with the time age, because one model doesn't have a paleomagnetic adjustment. Another is the different elevation dependency also produce different production rate. With increasing elevation, this also increases. But when they compare with Islet and Lal and Nesizumi, it is working a little better. What you see, it doesn't depend upon age. It goes all the way up. But however, what you see, the little dependency on elevation is still there. So their models are not perfect. They need more information and more data. So scaling scheme is the best that what it can do. So this is what they are doing. Another issue is geomorphological issue, what we have discussed, the inheritance. So if there is any inheritance, measured time will be always greater than true exposure. Another thing, exhumation measured time will be less than true exposure. Erosion, if there is any erosion, measured time will be less than true exposure. Shielding, measured time will be less than true exposure. What we see here, the geomorphological issues, mostly they are directing towards the less age. Like cosmogenic, we can underestimate, there are more reasons to have underage samples, like we can measure lower ages. But what we see in past, cosmogenic age are overestimating. But the paper says the OSL age are much younger than the cosmic age. So what we see, only the reason is inheritance. The measured time will be greater than true age. Otherwise, we see the all factors will reduce to the less, underestimation of the age. So what I have shown already this, because this factor geomorphological process, the mostly geomorphological process will give the less age rather than accept inheritance. So suggestion is that if we use pair nuclides, we can remove, at least we can identify. The pair nuclide means here we use the aluminum and beryllium. So what you see here, this is the ratio of aluminum beryllium and the y-axis. Here and there is the beryllium atom. And you see because they have a different half-life. If you have a erosion, let us say, if you have an erosion, then you will end up with on these lines. And if you have a burial, so your sample will go on these lines. So at least if there is any erosion, high erosion of your sample, you can identify this sample eroded more or this sample exhumed, then these numbers will come down on these lines. So at least exhumation and erosion can be identified by using pair nuclides, but inheritance can't be. Inheritance is tricky. So same here, this is what I did from the Cronus. So let us say, for example, this sample is down, so buried, and these samples are okay. So because near this, here there is no erosion. If you go down, there is erosion as well as it may be buried. Another method is geomorphological correction. We can't do anything about, whatever data is coming. But what we can do, the geomorphologically you collect the number of samples from the one site and see this group, how this follow the peaks. So you distribute and you make a function by using kernel density function, and you see how many Gaussians are there. So if it is too far, so that is more likely it has an inheritance. If it is too low, that means more likely it is eroded or there is a problem. So at least this can minimize the geomorphological issue. But other than that, I don't know. This is the best right now we could do it. So this can minimize the inheritance and exhumation by multi-Gaussian fitting. Minimize. I cannot say this is completely remove the inheritance, but this can at least minimize. So what we observed, different model predicts different production rate, and we see the at least 20% change. So dependency of models are different with respect to polymagnetism and elevation. Model still need more calibrated site to improve upon the cosmogenic accuracy. So what I suggest, use of pair nuclide can identify erosion and exhumation, but not inheritance. Removal of inheritance is tricky, and one can minimize by using Gaussian separation method. So now I will discuss the OSL basics. So what OSL has issue. So this is not like only cosmogenic. OSL also have some issues. So these are the key reference for OSL and how OSL works. So we estimate the time by measuring the accumulated dose and dose rate. Accumulated dose is in sample. It is stored in the form of luminescence signal, which is proportional to the dose strength. And then we measure the radioactivity, which provide the dose rate. So typically, if we see typically sediment sample has 3 gray per kiloyear. Gray is nothing but the measurement of dose. 3 gray per kiloyear. That means in 1000 year, sample will have a 3 gray of dose and equivalent signal. So as you go on, the dose will keep on increasing, and this will keep on increase the luminescence signal. I'm not going to much detail in luminescence, but I will show you some problems. So what we do, we measure signal in terms of OSL, optically stimulated luminescence, and thermoluminescence. What we use, we generate the growth curve with dose versus luminescence signal. And then, because the sample we haven't given anything, so this will give a state signal, and we interpolate laboratory generated growth curve. And this will give the time information. So this will give the time information, how much dose it has and how much depend upon the luminescence signal. So, but what we see, there's a huge application of luminescence. Wherever you see sediment or growth of some crystal, you can apply this method. So, but there are problems. So bleaching. Let us say sediment see the sunlight, and we can date the sediment. So what we date actually the last sun exposure event by using the luminescence dating. So what if hours? So let us understand from this cartoon. So there is some geological dose in the sediment, and when sediment traveled by wind or by fluvial system like a river, water, or wherever it travels, it sees the sunlight. So when it sees the enough sunlight, it's completely bleached. So this will start from zero. But when it doesn't see enough sunlight, that means sunlight is not available. What we see, it is not zero, so it has some inheritance, and it will give overestimation. Once again, I want to emphasize here, this paper, 2020 Shukla et al., even bleaching is there. Let us say in fluvial system here in glacier, we expect there is sample may not be bleached. That means if this is not well bleached, the sediment sample should overestimate the age. So that means it should be in higher side, not lower side. But what we see against the cosmogenic dating, cosmogenic dating is a higher side, and the bleaching is not expected. OSL should be higher side, but they are under the cosmogenic. They are, less than the cosmogenic dates. So even this bleaching is not there. We should expect overestimation this is, but it is not. They are even less than the cosmogenic dates. So what we see, another issue with Himalayan case, quartz and feldspar has a dim signal. That means it had whatever luminescence should be produced by a given dose, it doesn't produce the luminescence signal per unit dose as other sediment sample produce. Other sediment sample means if sample is very good, if you take a Thar sample or you take it from South India sample, these samples are very bright and they give million counts of the signal. But if you go to Himalaya, these samples are very dim and they have an issue with the sensitivity. I will give you some. It is the quartz from Himalaya. What you see, these are the number of luminous OSL signal, number of OSL counts. What you see, the nature is sitting over somewhere in the background. And similarly, one test dose generally we give less than a natural dose. Less than dose. So what you get, you see, you have a very less amount of signal. If you can end up at the random numbers. And result of this sample, at least what you see, is all chaos. Because what you see, the test dose has a lot of background, and here OSL natural dose also inside the background. So when background compare the background, you will end up with the random noise. Random distribution. So it has no meaning. This can be a coincidence. It is like it is following the rejection criteria. Because what happened, the sensitivity is a big issue. Here, the sample doesn't give signal. Only natural doesn't give signal, but when it started heating and it started producing again signal. So these are the two samples. You see, they all everywhere is random numbers. So what we note here, growth curve dose versus intensity may be coincidence. Having a growth curve doesn't mean ages are correct. Rejection of many ages of sample are not correct criteria to interpret results. When signal is dim, one cannot rely on OSL ages because naturally we don't know if it is inside the random numbers or background. So the sensitivity changed during the measurements. Now I will show you some problems. So there is how we separate quartz and feldspar. We separate by a density separation. So what I observe, when we were using a sample, this was either sinking or floating, but quartz and feldspar has a different density, but this sample doesn't sink or doesn't float. I mean, it doesn't separate the sample. It only sinks when you put a 2.65, or it floats when you put a little less than density. So we were seeing in case of radiofluorescence, because here the luminescence signal, what you see, this is nothing. There is no signal. So we were thinking, coarse grain, why they are dim? Impurities are not present, or crystal growth was not proper, or weathering was not proper. So what we see, when we see, okay, coarse grain is not good, let us check fine grain. When we see the fine grain, we see the enough amount of signal. So what we see, why not let us explore what is there in the crystal. So XRD, it need powder and give the mineral composition, only mineral composition, but not individual grain information. Similarly, SEM also we have done. So it gives only information like how much elements are having, but there is no other information, which was like it has a feldspar and it has a quartz. But there is no information. If it has a feldspar, it should give signal. If it has a quartz, then it should give a signal. Similarly, QEMSCAN, mineral composition of here, this machine give the mineral composition as well as individual grain what it has. It map whole grain by pixel, and it gives the information about your grain. So we went for QEMSCAN. It is the laboratory in Australia based. So what you see, this is giving you, the quartz, feldspar, and how much they are present in. See, you see quartz, feldspar. Feldspar is something like 10 to 20, quartz is 30 to 50%, but there is no signal. And what you see here, again, this will not give you any information. This is coarse grain. It has a quartz and it has a feldspar, but there is no signal. So how we can say this sample is bad or good? So here is the very healthy, good signal, which is giving good signal, and it is coarse grain. What you see, lot of feldspar, greenish K feldspar, and this is some mixed. But what was the bad sample, coarse grain, what we have, which was not giving signal, if you see the coarse grain, it has a mix of everything. It is like an assemblage of every mineral, and everywhere it is there. And this is not giving any signal. But now question is why fine grain is giving signal. So when you see the fine grain, this same bad sample, you see all minerals are separate. There is no assemblies. They are not mixing. So here fine grain is giving and bad coarse grain is not giving the signals. So here is the issue. I didn't get the time to find the reference. There is a paper by Suchinder et al. He did the sensitivity work And then he found the grains from Himalaya, they have a water inside. And when they heated up, water is gone and start giving the signal. So these bed samples sensitized something like 9 to 10 times. When you use the heating, then this will sensitize. So that means once water is gone, they start getting sensitized. So the natural signal has a problem here when you first measure. So this kind of sample will have a problem. So what we should do, the better alternative is fine grain. So what we observe here looks like coarse grain, not so pure even after density separation. Fine grain sample behaves better than coarse grain in terms of signal. I mean, this would be better to use, the better than coarse grain at least. The QEMSCAN mineralogy analysis suggests that fine grain are in its pure form, not assemblies. So this can serve better. So finally, to summarize my talk, the cosmogenic what we observe, different model predicts different production rate, and dependency of model are different with respect to paleo-magnetics and elevation. Models still need more calibrated site to improve upon the cosmogenic accuracy. Inheritance, exhumation, and erosion. Geomorphological process will introduce unwanted offset. These geomorphological process also introduce unwanted offset. The OSL looks like coarse grain, not so pure, even after density separation. The fine grain sample behaves better than coarse grain in terms of signal and would be better to use. So few suggestions, OSL and cosmogenic method both need improvements, and dating and field groups should come together and they should exchange the knowledge. They should teach each other, because sometimes the people are working in lab, sometimes they should also have a field exposure. And field exposure people, they should also understand what are the problems. So I think this is the best platform. We should discuss easily and openly whatever problems are. So thank you for listening me. Okay.
Thank you very much, Dr. Murari.
No
now you
problem.
can stop your screen.
I can stop my screen now.
Please.
Okay. Just a second. Can you see my screen is gone?
Yes, sure. Thank you very much.
Okay, thank you.
So we have not much question. Only one question is there. That is also from a YouTube viewer, Bilal Sonu. He is asking, sir, what should be the required weight of quartz grain from each sample taken for measuring 10 BE and 26 AI aluminum, beryllium and aluminum? You can see in chat box also. The question is there at the end.
So this question is, okay. Let us take, hello everyone, can I see? Okay. Kindly click the hide button, okay. Which one? Can you say something?
The last one. Sir, what should be the required weight of quartz grain from each
What should be the required weight of quartz grains from each sample taken for 10 beryllium and 26 beryllium? Usually 20 gram pure quartz is okay. Usually 20 gram pure quartz is okay, but sometimes if your sample is not so old, then production is very less. So sometimes we use a higher amount of quartz too, because the concentration cannot be measured if it is too low concentration. So usually 15 to 20 gram quartz is enough.
Thank you. I think one more questions.
Yes.
Some questions are coming. So
Mm-hmm.
please explain again about the low cutoff rigidity at high latitude.
Okay, please explain again about low cutoff rigidity at high latitude. So, shall I show the picture? Low cutoff rigidity at high latitudes. because the magnetic field line, they have to cross very small amount as compared to the low latitude. So there is a less cutoff and atmosphere pressure.
So actually, Madhav,
Yes, please.
if I can comment on that, actually, so the magnetic field is very high at poles.
No, magnetic field lines. You see the magnetic field lines.
Correct. So
Magnetic field line is the important. They combine there at the pole.
Yeah, so the magnetic field is higher at the pole, right?
But magnetic field number of lines are not more. They get parallel to it.
Number of magnetic field lines are more at the pole in comparison to other places, right?
Right.
But the reason here, the low production rate, low cutoff rigidity, because the angle between the field lines and the cosmic rays. So they are at the poles, they are parallel. However, at the equator, they are perpendicular to each other.
This is what.
Yeah.
Yes, angle of incidence is perpendicular. So there is cutoff it is very high.
Correct. At the equator, so that's what there is.
Right.
And can you also pair 53 manganese with beryllium 10?
With what?
With beryllium 10.
Beryllium 10, then? Say it again.
So there is another question. Is it possible to use other CRNs in pair, such as 53 manganese and beryllium 10?
I see the magnesium, nobody has used magnesium, but 10 beryllium and neon and aluminum are generally used for the CRN dates. And sometimes we go further the equal half-life. Near what equal half-life is there, then we use those pair nuclides, not like a separate.
But the beryllium has double the half-life of aluminum.
Right. How much is magnesium? I have to check it. How much is magnesium? How much is magnesium?
Magnesium is, I think that is close to beryllium probably. I don't know.
There may be some other problem, but I know about like mostly aluminum and beryllium and neon they have used.
The manganese is 3.7 million here, so double of beryllium.
Double of beryllium. So
the main reason actually is that in quartz only you can find beryllium and aluminum both. In one sample you can have two CRNs. So that's why they are preferred to use.
So you think about, okay, then maybe I have to look for it.
Yeah.
Because mostly I think I have seen the aluminum and beryllium as well as neon, not anything like magnesium. Okay. Do you think
one more question by Dr. Binita Fatiyal. Can you please?
Do you think?
Yeah. Hello. Madhav, I have a question. Yeah, thank you for this interesting talk. And I just had a query that, there is so much of published literature, especially I'm talking in reference of the Himalayas. So they've used Cosmogenic, they've used OSL ages, and, it goes.
That's right. So your question is, do you think all the published A's need to be revisited and especially from the Himalaya? You see,
is it?
No. I won't say this, but the thing is, the models are, they have a limitation. Models have a limitation. If they improve, somebody will revisit the data from the published work. But OSL, I think OSL, if they have no problem of sensitivity issue, what I have suggested that if there is a sensitivity issue in your sample, please check it and then go for it. If there is no sensitivity issue in your sample, but I doubt Himalayan sample has a sensitivity issue.
Okay.
Can I comment on this?
Yeah, please, Pankaj.
Yeah. Actually, revisited is okay. Revisiting can be done because earlier we used to think the half-life of beryllium was considered as 1.5 million a year, but now recent data says that it's 1.39 million a year. Okay, so the ages which has been calculated considering half-life 1.5 million a year. So those ages may change a little bit, but redone is not required. Once you get the data, once you know that okay, this much is the concentration of beryllium-10, probably you can change. Applying new half-life, you can revisit the exposure ages. That probably can be done.
Okay, thank you, Pankaj. Thank you, Madhav.
Yeah, one more question from the YouTube viewer. Dr. Madhav, what is the opinion about the overestimation of age at high altitude Himalaya, where we have glacial advancement and recession?
At higher Himalaya, see, overestimation of cosmogenic or OSL?
I really don't know because it is from the YouTube viewer. It is written there in
No
the chat
problem.
box.
Yeah, if he is talking about the OSL, the Himalayan sample, if they are overestimating, that has a bleaching issue. But Himalayan sample, I feel the sensitivity is the big issue than the bleaching. Because sensitivity, the sensitivity is the big issue. So sensitivity will not overestimate in case of OSL. But in case of cosmogenic, high altitude or low altitude, the model, whatever model we have, we can predict based on that. So what we see the models predict something like 20% offset. It goes into the estimation of age. So according to the models, it may be something like 20%, which is not big, unless it doesn't have an inheritance. Your sample is clean, then you won't have a problem. But if the sample is not clean, it has an inheritance problem, then this will be overestimated, because inheritance can be anywhere.
Thank you very much, Dr. Madhav. And I think there is no more question. So I would just like to thank you for a very informative talk about this cosmogenic material.
No problem.
And now, on behalf of AOQR, I would like to invite Dr. Jyoti Srivastava for formal vote of thanks.
Thank you, Dr. Shah. A very good afternoon to everyone here. After listening to this interesting talk by Dr. Madhav Krishna Murari, I'm sure that the webinar today has been fruitful and highly informative for all the participants here. Thank you, Dr. Murari, for accepting our invitation for the talk. And along with that, I wish to thank the Director BSIP and the President AOQR, Dr. Vandana Prasad, Vice President Dr. Pradeep Srivastava, Secretary Dr. Binita Bhartiyal, Treasurer Dr. Santosh Shah, all the other founder members for their constant support and encouragement. I would also like to express our gratitude to our honorary members, Professor Ashok Singhvi, Professor Vishwas Kale, Professor Hema Achutan and Professor L.S. Chamial for their guidance and support in bringing up this association. I also wish to thank our ECR team members, Dr. Senthil Kumar Sadashivam, who is behind the designing of this Quarterly Chronicle newsletter issues and the flyers of this webinar, and Dr. Linto Alapat, Dr. Manoj MC, Dr. Trina Bose, Dr. Ayush Srivastava and Akash Srinivas for making this webinar a success through their support. I extend my sincere thanks to all the quarterly scientists, faculty and students for participating and showing great response to this webinar series. The program has been successful only because of their cooperation and enthusiasm. I also wish to thank the BSIP IT team, especially Mr. Katiyar and Dr. Mille for making this webinar successful. Thanks once again to Dr. Santosh Shah for moderating the talk and Dr. Trina Bose for managing the questions and answers. At last, please fill up the feedback form, which has already been provided to everyone, as this will help us in improving the upcoming sessions. So now we will meet again on 28th of September for the 4th webinar talk. Thank you once and all.
Thank you.
Yes.
Shall I close it?
Okay, thank you. Thank you very much. Yes, please. Thank you very
you,
much, Dr.
Madhav.
Murari.
Thank you so much. Thank you, every participant. Yeah. So we call it an end. Thank you.
Okay, thank you,
Thank
everyone.
you. See you next week.
Bye.
Thank you.